Okay, so today I'm going to go over the Unit 9 study guide. Please note that the study guide is designated by different types of stoichiometry. So like this first page here is specifically for mole to mole. Okay, and that's what we're going to start with. So I'm going to go over a problem from each section of the different types of stoichs here in this video. So for number 1, our first step is to go ahead and balance the chemical equation. So let's go ahead and count how many atoms we have of each. I have 1 aluminum on the left, 2 oxygens on the left, 2 aluminums on the right, and 3 oxygens on the right as well. Now, if you take a look and try to balance your aluminums right away, you may want to multiply that aluminum on the left by 2 to make it balanced, which is great. However, if you notice, your oxygens are currently an uneven number. You have a 2 on one side and a 3 on the other. So let's go ahead and get our number of oxygens up to be 6 total. So I'm going to go ahead and multiply the oxygen on the left by 3 and the oxygen on the right by 2. Okay. Now this is going to go ahead and affect your aluminum then. So now we have 2 times 2, which is a total of 4. So then I'm going to go ahead and multiply the aluminum on the left-hand side by 4 as well. So now we should have a nice balanced chemical equation. Letter B then states how many moles of aluminum oxide will be formed from 17 moles of aluminum. So what's given is the 17 moles of aluminum. That's what we're going to start with, and we're trying to find moles of aluminum oxide. Please note that we're given moles and we're trying to find moles, so this is why it's a mole-to-mole type of stoichiometry problem. In order to go from moles of one compound to the moles of another, we have to use our balanced chemical equation, because this is like our recipe. Our recipe is able to go from different compounds to different compounds. So first step, let's go ahead and start with what we're given. We have 17 moles of aluminum. I'm going to go ahead and draw my nice little dimensional analysis table. Now please note that if I'm given moles of aluminum is going to have to go on the bottom. In order to determine how many moles of aluminum we have, we need to look at our balanced chemical equation. So from our equation, it says that for every 4 moles of aluminum, we have 2 moles of aluminum oxide, Al2O3, which is what we're trying to get into. So on the bottom, since I'm working with aluminum, I'm going to go ahead and put the 4 moles. And then on top is what I'm going to go ahead and try to find. So 2 moles of aluminum oxide. Okay, again, this particular step here is directly from your balanced equation. This is called your mole ratio. Once you have this setup complete, you can go ahead and now solve out this problem. Our moles of aluminum are going to cancel. We're left in moles of aluminum oxide, which is what we want to try to find. We're going to go ahead and multiply the top 2 numbers together and then divide by the bottom number. So divide by 4 here. When you equal this out, you should get an answer of 8.5 moles of aluminum oxide. Okay. All right. Next problem here, I'm going to go to the next page. So we're going to be working with now a mole to mass type problem. So again, I'm going to focus on question number 1, the first one. Please note there should be a little arrow between this. For some reason, it created a box. There we go. Okay. So first step, going ahead and balance. Our HGs are both 1 on both sides. Oxygen is 1 on the left and then 2 on the right. So I'm going to go ahead and multiply my oxygen by 2 on the left-hand side. This is also going to change the number of HGs. So I have 2 HGs on the left. So then I need to have 2 HGs on the right as well. So now it's balanced. Okay. And again, there's a little arrow here. This is a 2. This is a 2. All right, first problem here. How many grams of mercury 2 oxide are needed to produce 2.5 moles of oxygen? So find what's given, 2.5 moles of oxygen, and find what you're trying to get into, which is grams of mercury 2 oxide. Okay, again, this is a mole because you're given mole, to mass because you're trying to find grams type of a stoichiometry problem. Now, please note you cannot go from moles of a compound to grams of a different compound directly. You have to have that middle step. This is a 2-step problem. So we're going to start with what we're given, 2.50 moles of oxygen. Okay. okay? Now, if you're in moles of oxygen, you can go from moles of oxygen into then mercury to oxide using our mole ratio. So the very first step is going to be the mole ratio. Again, this is going to come directly from your balanced chemical equation. So for every 1 mole of oxygen, we have 2 moles of mercury oxide. Mercury oxide is HGO. That's mercury oxide. Okay. Our units of oxygen, moles of oxygen, are going to cancel. We're left in moles of mercury oxide. We have to do one more step because we're trying to find grams. In order to go from moles to grams of something, you have to use the molar mass. Molar mass comes directly from your periodic table. So you need to look at mercury. Mass of mercury on your periodic table is 200.59. Oops, ran out of room, 0.59. And then oxygen has a mass of 16. You only have one of each, so you just need to go ahead and add those things together. Okay, you are going to end up with a molar mass of 216.59 grams per mole of mercury oxide. Now note your units here as grams per mole. So you could also say that for every 216.59 grams of mercury oxide, you have exactly 1 mole of mercury oxide. So now we're in moles of mercury oxide, so that means 1 mole of mercury oxide can go on the bottom here, so that way the units cancel. And then I'm going to go ahead and put the mass that you calculated, 216.59 grams of mercury oxide, on top. And that's the unit that you're trying to get into. So perfect. Now we're going to go ahead and solve this problem. So multiply everything on the top, divide everything on the bottom, and you should end up with the answer. It's going to be pretty big, 1,083 grams of mercury oxide. Okay, we're in grams. That's exactly what you're trying to find. So then this would be your final answer. Okay. Next page, mass to mole. Here I'm already giving you a balanced equation, which is pretty nice. So that's one less step that you're going to have to do for this particular problem. So let's just go ahead and jump right into B. So it says, if you start with 50 grams of hydrogen, how many moles of water, H2O, will be produced? So 50 grams of hydrogen is what's given, and then moles of water is what you're trying to find. Again, this is a mass to mole type of problem because you're starting with grams, which is mass, and you're trying to find mole. Okay. Again, we cannot go from mass into moles directly of 2 different compounds, so this is again a 2-step type problem. We are going to start with 50 grams of hydrogen. Now, we can only go from mole to mole between compounds. That means we have to get this grams of hydrogens into moles. In order to do that, we need to, again, use our molar mass from our periodic table. Okay, so hydrogen has a mass of 1.01, and there is 2 of them because it's H2. So then our molar mass for hydrogen is going to be 2.02 grams per mole. I can use this information to go ahead and now plug it into my problem. So if I'm given grams, that means grams in this case has to go on the bottom. So 2.02 grams of hydrogen for every 1 mole of hydrogen. Okay. Now our grams of hydrogen are going to cancel. We're left in moles of hydrogen. Because now we're in moles, we can go to moles of water directly by using our balanced chemical equation. So if we're in moles of hydrogen, there are 2 moles of hydrogen from our equation, and there are 2 moles of water from our equation. We're going to go ahead and equal this out. So multiply the top, divide by the bottom, and you should end up with 24.8 moles of water. That's a lot of water. Okay, next type of a problem is a mass to mass. So this is the longest type of problem on here. This is going to be that 3-step problem because you have to find 2 molar masses and use the mole to mole ratio. So question number 9, we first have to balance out this problem. Again, this box should be an arrow. We have 2 nitrogens on the left, 1 nitrogen on the right. So I'm going to go ahead and multiply that by 2. That is going to affect our hydrogens, however. So we have a total of 6 hydrogens. So I'm going to multiply the hydrogen on the left-hand side by 3 to get a total of 6. And now this is balanced. Okay. Our problem, if 56.0 grams of nitrogen are used up by the reaction, how many grams of ammonia will be produced? 56 grams of nitrogen is what's given. Grams of ammonia is what we're trying to find here. So we're going to start with 56.0 grams of nitrogen. Again, we cannot go from grams of nitrogen to grams of or moles of ammonia. We need to get this grams into moles. So again, looking at our periodic table, we're going to calculate the molar mass of nitrogen. Nitrogen has a mass of 14.01. There are 2 of them, so then the molar mass for nitrogen is 28.02 grams per mole. We're in grams of nitrogen, so that means 28.02 grams of nitrogen will go on the bottom, and then we have 1 mole of nitrogen that goes on the top. Please note that this right here is your molar mass, and on the top will always be 1 mole. It's never going to change. Our grams of nitrogen are going to cancel. We're in moles of nitrogen. Because we're in moles of nitrogen now, we can use our balanced equation to go into moles of what we're trying to find, which is ammonia. So that means from our balanced equation, here I'll change the color here, for every 1 mole of nitrogen, we have 2 moles of ammonia. Ammonia is NH3. Okay. Our moles of nitrogen are going to cancel, and we're left with moles of ammonia. Our very last step now is to go from moles of ammonia into grams of ammonia. And again, we're going to have to use our molar mass from our periodic table. Okay, so we have 1 nitrogen, which is 14.01, and we have 3 hydrogens, each having a mass of 1.01. So then our total molar mass here for ammonia is going to be 17.04 grams per mole. Okay. We're in moles of ammonia on top, so that means 1 mole of ammonia is going to go on the bottom for every 17.04 grams of ammonia. We're going to go ahead and equal this out. Again, multiply the top, divide by your bottoms, and you should end up with 68.1 grams of ammonia. That should be your final answer here. Okay, last type of problem is the limiting reactant. So the limiting reactant, in this particular case, we have to balance the equation, but you're essentially doing 2 types of stoichiometry side by side and comparing them to see which one is going to run out first. Okay, so balancing this equation, we have 2 nitrogens on the left, 1 nitrogen on the right. So I'm going to multiply that by 2, and then that also takes care of our oxygen. So that one's pretty easy to balance. Okay, we are given in this scenario 65.0 grams of nitrogen, 70 grams of oxygen here, and it's asking what is our limiting reactant. Okay. So we're going to start with 65 grams of nitrogen. We're going to do 2 problems technically. So if I just write out the next type of problem, we're going to start with 70 grams of oxygen. Okay, so notice here that I have 2-dimensional analysis, 2 stoichiometry setups side by side here. That's exactly what you're going to want. And actually, I'm going to change the color of that second one so that way you can clearly see it better. So 70 grams of oxygen. Okay, focus on one at a time here. Don't do them both. So if we're in grams of nitrogen, we want to get into moles of nitrogen because then we can compare between different compounds. Please note that whenever you're trying to find the limiting reactant, you're essentially trying to find, okay, which one is going to create the lesser amount of our product. Your product in this case is NO. There is only 1 of them. So this is the item that you're trying to go into for both of your given grams. Please note that you only really need to go into moles, because you can compare however many moles you have of your product to moles of your product given your other reactant. Okay, so that's our goal. So our goal is to try to figure out, if we're given the grams of both of these substances, how many moles of NO are we going to be producing? So if you're in grams of nitrogen, again, you got to use the molar mass to get it into moles. The molar mass of nitrogen is 28.02 grams for every 1 mole. Okay. Now that we are in moles of nitrogen, we can very easily go into moles of NO by using our mole ratio from our balanced equation. Grams of N2 are going to cancel, so then for every 1 mole of N2, we have 2 moles of NO. Okay, moles of nitrogen are going to cancel, so we're left with moles of nitrogen monoxide. When you go ahead and calculate this out, you get 4.64 moles of NO. Okay, so that's just from the nitrogen. That's how much it would produce if we had that much nitrogen. Now comparing it to the oxygen. So we're going to do the same exact setup. So first step, change grams of oxygen into moles by using the molar mass. Oxygen has a mass of 16. There's 2 of them, so 32.00 grams of oxygen for every 1 mole of oxygen. Okay. Now we can go from moles of oxygen into moles of nitrogen monoxide. So for every 1 mole of oxygen, again, I'm getting that from your balanced equation, there are 2 moles of nitrogen monoxide. Again, we only need to go into moles here, so that way we can simply just compare. So then go ahead, multiply, divide. You should end up with 4.38 moles of NO. So taking a look at these 2 values here, which one is smaller? It is going to be 4.38 moles of nitrogen monoxide. That means this is the most we can make before we start to run out of things. If you remember that root beer float example where we ran out of root beer and we still had ice cream left over, this is the same idea. In this case, what we're going to run out of, though, is our oxygen. So that means O2 is the limiting reagent. We're going to run out of that first because we're not going to create enough product compared to N2. Okay. And that's all you really need to figure out. You just need to tell me what is the limiting reactant. Of course, you do have to show your work on these different problems. That's how you get the most amount of your points on the assessment. But the biggest thing here that I'm looking for is, what is your limiting reactant? What's going to give you that lowest amount of product? Okay, give me a second while I erase here. The very last page then is going to be mixed, so you really just have to pay attention to what you are given and what you're trying to find. So you have to balance first, but then for like letter B, it says you're given grams and you're trying to go into moles. So that would be a mass to mole type problem. Letter C, you have grams and you're trying to find grams, so mass to mass. Letter D, you have moles, you're trying to get to grams, so moles to mass. Letter E, mole to mole. And then the last one, again, you're trying to figure out that limiting reactant. So you got to set up 2 problems. The only thing that I'll mention here is that one of them is in moles, one of them is in grams. So for this one right here, where you have 4.00 moles of C3H8, you actually have to do less work, because all you're doing here is going from moles of this compound to moles of one of your products from your equation. And please note, it does not matter which product you choose as long as you're doing the same product for both of your problems. So for instance, if I wanted to go into moles of carbon dioxide, I would then focus on moles of carbon dioxide and I would finish out this problem. But you could also go into moles of H2O, and that would still be correct as long as when you're setting up your 119 grams of oxygen, you eventually are still going into moles of water in this particular case. So like I said, it doesn't matter which product you're going into for a limiting reactant as long as you stick to that same one. And that is all.